Okay, in this video, let's try and make a joint control plugin. Basically, we'll be moving a joint using different methods that's available in Gazebo Sim. Okay, so this is that joint. This is blue color joint. That's joint number one. This green and blue are attached with joint number one. So we are going to move this joint, and we'll understand how to make it move. Okay, so there are three ways to make it happen. One is velocity, other is force, and position. There are three ways that we can use it to make it move. Okay, so let's try and understand how to make this joint control plugin. This is very common plugin that you will need to control robots, joints, and other things, or some any other object that you are creating. Mostly you have the joint, either you will have a revolute joint or you will have a prismatic joint. So I'm going to show it with revolute joint. You can do same with prismatic joints. Okay, so we first need to find this identity. How are we going to find this identity? So now we are going to use a different method called identity by component. Okay, so what are we doing over here? We first check that the parent entity is model, and then we have a name attached to that thing, and then we have joint component attached to it. So let me show you that file, the joint control one, and I will explain you a little bit what are the things over there. So if you see this mega joint T on this, you will see two joints link. So this two joints link, the ID, if you see the joint entity ID is 19. How will get this entity ID number 19? So what are we using over here? We are using three things from here to make it, for our use case, to make it work. Firstly, we are using this name component, and then we are using this parent component. So who is the parent entity? So the parent entity of this is this model. This model is the parent entity, right? And other one, we are using this joint entity. So the even joint, sorry, this joint component. So this is also a component. So we are using this joint component, this name component, and the parent entity. So if we are saying if all of these three are there, then we are going to do what? Then we are saying that if these three are there, then we are going to get the joint. So if I show you who is the parent of this joint entity, if you see the parent entity is 8. So this is the parent entity and its value is 8, integer value. Okay, so what is saying over here is basically entity by component is a method by which you can use component to get the entity. So we are using the parent entity is the entity. So that means the entity coming from config is basically this entities will only come when your config is attached to the model. Okay, so this firstly is attached to model, and then this we got the parent entity, then name, and we are getting the name of this joint one. We are going to give it from SDF file, and then we are getting the component joint. So even joint is a component as well as an entity. The same way model was a component and model is an entity. Okay, so it's the same logic. So now as we want this parent entity to be model only, how are we going to make it happen? We use here something called entity has component type. So it takes entity and then it takes the component ID. So if you want to give any component ID type, then it's very simple. It's written component model, then you add this resolution operator and type ID. Then you'll be able to get the stripe ID value of it. It's valid for all the components. You can test it out. Okay, so here we are doing entity has component type. So it is saying if entity has this component type, then only we are going to make it work. So if this comes out to be false, then your plugin is not going to load and this gazebo error is going to showcase. So what it's checking is checking if model entity, if the entity that's coming from the config file, the config that we set up while making a system plugin, if that is there, then we'll use that entity to find whether it's a model entity or not. If it's not a model entity, then the plugin is not going to work. Simple. Okay, now the important thing is every time you started to write any plugin, you have to firstly check what are the components available around those plugin. So if you go onto this link and if you search for joints, then you will find those different entities, those are available for that plugin. Sorry, those components which are available for those plugin. So if you check what are the components that are available, joint force, and then joint force command is there. So everything that's written as a command, as I told you already, is everything that's written as a command is basically it's letting us to write on this joint force. It means it's letting us to write on this joint force. The command means that. So everything that's there on the command will use it to write onto the component. Okay. So if you see, this is one component, and then if you see what other are component, this joint velocity is component, but there is no position component. Remember this, there is no position command. There is no position command that has this. So how are we going to check for position? We'll understand that in a minute. So see, this message type is, their message type is double vector. Their message type is double vector, same for both of them. And then how many degree of freedom is there? According to that, they are going to assign those value internally. It handles this. If you read the details of this, you'll understand that. So how are we going to use? As we discussed, we are going to use three methods. One is velocity, another is joint, and then first one is velocity, another is force control, and the third one is, what is the third one? Third one is position control. So we use three of the method. And for joint control, for velocity control, for the joint, using joint velocity command. This is the component that we are going to use, and the unit of it, because for revolution it was the radian per second, that's basically the SI unit of velocity, angular velocity, and the type is vector double. Okay, so this applies velocity onto the component. So we'll first check if entity has component types. So the same ID thing that I told you, takes the ID, and if it is not there, then it's going to create. So generally what happens when you are making it for the first time, the command component doesn't exist. Then once it's created, then it's going to act on it. But if you don't do this, if you don't create the entity for the first time and start running this directly, it may happen that your plugin many times it doesn't work out and you won't be able to figure out what is the issue. So you have to be a little bit careful around this. Okay, so this check is this very simple. We are just using joint velocity command, and this command velocity, that's applying velocity. Same goes with the force. We are using joint force command, and here the force is torque. Basically it takes torque to make it work because it's force method, so it's taking torque. Okay, so in that also the same logic, that if entity does not exist, if component does not exist, let's create that component. Joint for component, we create that component for the first time, then we set it up. All these values are set to 0 initially. If once we are creating it, we just create them as 0 value, and then we are setting it, we set them as the value that we want. Okay, now these two methods are very easy. But the problem with force method would be that there is no direct way to calculate force. So if you know PID, we are going to use PID, but I haven't used entirely PID. I just use PD in this control. So PD is what you must have, if you are learning robotics, then you might have came across this PID control, because in robotics and in general control system, we use this PID a lot for controlling any joints or any actuators and motors and all those things. So basically this is a closed loop system where we add, this is just a fractional value. Okay, so we add this K and D to it, and it's very famous, and we take the feedback of the errors that's coming from this two, and we feed it back to our system. So based on it, our system works. So it's a closed loop system. Okay, so I hope you know PID. If you do not know, just read about it, and I can tell you a very good resource for understanding entire PID. So let's open this. If you go down, so basically this is the point, that the set target that you want it to achieve. For our case, we are setting the joint position, so we want to achieve it to this position. Then we'll tune this parameters KP, I and D. So in our case, we are just using KP, that P and D for our control. So if you move P, then gradually this is visual is very good to understand. Then gradually at a point it sets a difference, and and then start oscillating. See, it start oscillating. So you have to tune it to try to get it to as near as possible. Then if you use D, then this fraction of the initial jerk that's there, it's going to smoothen up the jerk. So it's smoothen up the jerk, but in our case we are not even using k, but we should use it, otherwise there will be a little bit of gap that's going to left over here. So how are the gap is going to fill? If we use k, then this gap is going to get filled. So it little bit jerks in the starting, so you can use this, you can do this sort of settings to get a much better value, and you can tune this up to make it work and have the least jerks that's possible. This is how every motors works. So this PID is very famous. I just showed you a visual example to make you understand how it works. So in our case, because this k directly multiplies to the error, and this multiplies to the velocity. Okay, so the code here is similar to that. So this is just we are on the target position, we are checking what is the difference between current position and the target position, and that is the error. Then we multiply p to that error directly, and for d we are using this current velocity thing. So current velocity, this both current position and current velocity, we can get it from the component by reading the current velocity and current position components of the joint. We can get these values, and that's how you get the torque. So basically this both values are going to differ based on the error on your system. So if the difference is more, then it is going to try to achieve it fast. If the difference is less, it is going to get smoother. So when difference are higher, they run very fast. When difference are lower, they try to go it near, and initially it jerks off. Because we are not using PID over here, so even we are going to have that little gap that I told you, it's still going to exist. Okay, that little gap will exist, but it's fine because we are just coding it up. But when you use, make sure you add I values into your code. So now, even if you get, so error, the problem with errors is that the one problem with error is that even when I started coding it, so one error is that, so when you get the torque value, it can sometimes happen that it can give you some random torque, very high torque, like 10 lakh 10k something, some random torque to make. So to make it not happen, we apply a limit saying that you have to be within this. So if it goes beyond this limit, then it's going to limit it out, so that we do not get this random values and we'll get a heavy jerk and your entire plugin will fail. Even your Gazebo Sim will crash because physics can't handle this 10 lakh sort of things. So in real world, you can never have 10 lakh Newton meters, right? So because of that, we are setting up clamping over here. So if you see, we are setting this clamp to have a mean and max value between minus max t and plus max t. So every value within this range is allowed. If it goes beyond it, then we are going to limit it up. And then once we are near the tolerance, once we are near the joint, for example, if your target is to reach, let's say 180 degree, and you're almost there in 179 degree, then we want it to stop, because this error is very less, even less than a degree, even less than a degree. I just give you an example. If this error is very less, we want the torque to go zero, so that our system do not jerk like this. It should not jerk like this between these two values. It becomes smooth. Okay, because of that we have to do this, so that it doesn't jerk. We are clamping it to zero once we are within the tolerance. So this is how the code works. And as we are going to oscillate between 2 points, we are going to oscillate between 180 degree and maybe 30 degree over here. So we are going to oscillate between these 2 points, right? So the logic is that we are going to apply over here that point, position A and position B, that's basically degrees, and in Gazebo we take radians. So in that case, what happens, once we reach this point, then we are going to wait for time t, let's say for 5 seconds. Then will again from here, after 5 seconds, we are going to give another target to go to this. So we are always going to keep on changing our target position based on what was the previous target. If suppose the previous pose were A, then we'll use current pose as B. And if the previous pose wasn't A, then we'll use it as A. This is just way to write triggering it up. So every 5 seconds or some whatever the time that we mention on wait time, it is going to oscillate between these two angles based on that. And because we have the time limit, it will get enough time to go there and it will get enough time to come back. So if it reaches there, then for example it reaches on 2 seconds and it's going to wait for 3 seconds, and vice versa. If reaches on 5 seconds and suddenly it's going to come back. So we try to make this arrangement such that it looks smooth, such that this motion to this motion looks smooth. I hope the logical understanding of it is clear to you. So this is what written on this entire code, that we are using this sim time to get the latest switch time. Then we calculate the ellipsoid. Based on that, we say okay, this much is time has passed. Like for example, this time can be 5 6 whatever second that we define on the SDF file. It can be any time. Okay, so based on that time, we say we'll change our target position and we'll use this latest switch time as this the current time. That means at this time we switched into point A or point B. Okay, so now let's look into the entire plugin code. So if you look, as I was saying, we are going to only attach it to model. So if you see on this mega T joint model, I've attached it to the bottom. I've attached over here. So what is this joint plugin? The first one is it takes the joint name. Okay, then there are three possible modes for it. One is velocity, one is force, one is position. And for velocity we are setting this command val up, and for command torque this is the value. So when you have force mode, it is going to use this command torque value, and when you have this position mode, it is going to use this all list of values that we just discussed. This is position A for position A, and this is position B. So within this two position is going to oscillate. So it's going to oscillate from 30 degree to 120 degree, and wait time that we just discussed, it is going to wait for 6 seconds in total. And this is the PID values that we add, and then the max torque and the position tolerance. We just discuss all of this right now, right? So this is what I have added on the parameter. Based on what angle you are using, you have to tune this PID values according to those PT and all those max torque tolerance and all those things, so that your joint motion looks smooth like this. Okay, so now if I go on to the code, the same parameters are defined over here. Command val, position X, wait time, target position, has initial time for setting up it for the first time, P max torque, P tolerance for position tolerance, last switch time, all of those are there. Now this is the config here. So we are using two interfaces on this code. First one is we are using this config and pre-update because we are reading and writing both, right? Because of that we are using this. Now this we have defined all SDF parameters over here. So either you can use velocity or VL, you can use force mode or F, position or POS. Now all these are for position related parameter. We define this, and then we just discuss entity by component. And also this is a link from where I got the idea of using this. So if you go on to this link, you can see the code on Gazebo. This is the same example. I use this to understand. Okay, so this is another way that we can use it for our purpose. So if you read Gazebo Sim, you will be able to understand, get more ideas how to use entity, how to use component. So the main purpose of this tutorial series is I try to make things more clear for you so that you can start reading this Gazebo Sim GitHub repository and understand more code and make new plugins. Okay, so now this is the joint entity by component. Then we are setting the target. Initially we are setting at point A for initiating, and firstly we are setting starting up with 0, and then on pre-update. For the velocity mode, this mode is basically enums. There are three enums that I'm using: force, velocity, and position. So if the enum value is about velocity, then we are going to use this and we are going to set the component and joint velocity command. And if it is force, we are going to set joint force command. Same goes with the, if it is position, then we set, for the first time we set this initial values over here. And then from the next time, the same time logic that we just discussed, we use that time logic on this code. Then we read the component, then we read the current position. How we read it? You remember this code, this is the same thing that we are using. So we read the joint position. If you remember this joint position, so joint position is over here. So if you see, joint position is here and it gives you, returns you a double value. Okay, so we are using same to get the joint position value. putting up the entity, and if that joint position component doesn't exist, then we create it. For the first time you have to create it, as I was saying, and then we get the data out of it. Component has this data variable, if you remember. So we check if it is empty, that may return and our plugin stop. If it is not empty, we use it for current position to get the current position. Same for velocity, we use joint velocity to get the joint velocity. This is all for reading, right? So that we can get the current joint velocity and current joint positions. And we are using the same component. If it is not there, we create it. And the error logic we just discussed. And at the end, the clamp torque we apply onto this plugin and it works. Okay, now let's see all the mode one by one. So currently this mode I've set it to velocity. Okay, now let's see firstly velocity mode. So if you see on this, the mode is set as velocity, and this is using that velocity that we have mentioned over here. It's 1.0. It's using this to run, so it runs. Okay, now let's change this mode to force. So if you write your SDF properly, if you give the parameter, then it's very easy to switch on between modes. Okay, now on this you will see it is loaded force mode, and for the force mode it is going to apply force, and based on the torque that you have mentioned on the command torque, it is applying the torque. This is 15 Newton meter. But the thing is, this model is very big. I've created a very big model to explain you this. I think this would be 10-12 feet. Because of that, it's running very slow even with 15 Newton meters. If it would be small, then even it will run very fast with 1 Newton meter or something. So it runs very slow. Okay, now at the end, let's see the position mode that we just discussed using PD control. So let's change it to position mode. And as I was saying, I have tuned this all this parameter based on the target that I want to achieve. This I'm oscillating between these two position, 30 degree and 120 degree. I have written their values in radian because we are iterating between these two values, and then the wait time accordingly I've set. So this all parameter can keep on changing based on your use case. Okay, so you have to tune it every time. So this is very realistic. How real motor get tuned, you have to tune your PIDs of the motor so that it perform the way you supposed to want it without jerk and it performs smoothly. So this matches up realism little bit. Okay, now let's launch this up. So I've added some print and you'll start getting this prints. So you'll see now motor, the joint has reached this. Now it is going to that point to 120 degree, and once it reaches this, it waits for some second because 6 is not done, then it comes back. So it oscillates between this 2 point. It oscillates between these 2 points, and if in some case if I increase the torque, you'll see it, and because we added it to stop when it comes very close, then we do not see that jerking motion happen. Otherwise we'll see that jerking motion happen. For example, now let's increase the torque. See, it is going more faster now because we are applying more torque, right? It is applying more torque. So this is how it works. Oh, still it applies less torque because the P value is less. So if I increase the P value and even have increased the max torque, it will start behaving very odd. See, just once when it switches up, it's now moved little bit faster, right? Even it has more torque. See, it's having very much more torque because we increase the P. Because of increasing that P, that graph got very much fastly achieved that target, right? So based on how you want to play with it, you can tune off your parameters to make it work how you want it to. It's just that you have to spend some time tuning up this parameter to make it work smoothly. Okay, so this is how we discuss all the three methods: velocity, force, and position. So even now you understood how to make joint control work in Gazebo Sim. Okay.